Good morning, everybody. Hopefully you got, well, those of you logged in got the new link. And if there's somebody here that's in the group me, I wouldn't mind sending this link in there. You know, I know somebody,
Okay, so it was updated in the system.
I'm sure
Okay.
somebody didn't get it.
Okay. Thank you.
All right, let's see. Let me go ahead and share so we can get started. Oh, let's see. All right. All right, it's time to go. All right, so we talked about on Friday the 4 types of reaction: substitution, elimination, addition, rearrangement. We talked about curved arrows. We talked about the types of arrow bond making and bond breaking processes: homolytic, homogenic, heterolytic, heterogenic. We talked about quite a bit actually. And then we started with this example of an elimination, and we went through the mechanism. So I actually want to do that with the rest of these too, because it's going to help us when we get to the other part of this assignment. So let's go ahead and take, let's take this one. We're going to walk it down. Y'all all right with that? I'm going to take the silence as a yes. All right. So look at this reaction. What do you think happened? What does it look like happened? And let me refresh you. This is a skeletal structure. So that hydrogen that's right here is not shown, but it's there. So what did I actually do? Like, what does it look like? Here's a hint. If I start with a pi bond, you can see the pi bond here between carbon and oxygen. Right? A pi bond can only do addition. You cannot do substitution with a pi bond. Right? So if you look at the product, you can see right away that this has to be an addition. What did I add? What does it look like I added? So what's different on the
another bond?
Okay. And what atoms did I add? Let's think about that. I agree with you that we did add a bond. We added a sigma bond. I agree with that.
We added hydrogens.
2 hydrogens, because over here there's no hydrogens. Is that right? And then over here I got a hydrogen on right here on oxygen, and I have another hydrogen right here. So I added, in essence, I added H2. So let's think about that. Now this, what I'm getting ready to show you is not necessarily how this happens, because to add H2, you normally need like a catalyst, like a transition metal, palladium, platinum, something like that, ruthenium, iridium, some transition metal. But in this case, I'm going to show you like a simplified version of what happened, so we can actually just understand the addition part. So if I have a H here and an H here, if we add to the pi bond and then use the pi bond to pick up that proton, that's exactly what happened. Or that's what it looks like happened. So I added H2 across that pi bond. Now it probably happened through a different mechanism, but the idea is that it's an addition. Right, I added some nucleophile to the pi bond or to that carbon where the pi bond is between carbon and oxygen, and I broke that pi bond. Right, so it's an addition. Questions about that one? And this is it's plausible, meaning it could happen a different way too. But for the scope of what we're trying to accomplish right now, we'll go with this. All right.
So it's the
Well-
opposite of the other reaction that we learned on Friday, which was elimination.
Yes.
Okay.
Right, because if you think about it, if I take this and I remove, let's say I take off H2, and let me make it plain. Let me see if I can wipe this out, and then wish I had the same color as the paper. It would look nicer. But if I did this, something like that, right? Where this pair of electrons came here and this pair of electrons went here like that. That would give me back my start material, that plus H2. Is that right? So
Yes.
addition and elimination are the reverse of one another. All right, let's take another one of those examples and walk it down. Let's do this one. Yeah, instead of trying to crowd it. Right.
So for that other,
Go ahead, Eli.
for the other one, would it be polar or radical?
Oh, this is radical. I'm sorry.
Okay.
No, I'm sorry. This is polar. So everything is hetero, lytic, or genic. So if I make a
Okay.
bond, it's heterogenic. If I break a bond, it's heterolytic. Great question. And that's a really good question in light of the next example, because that's actually, I'm going to show you a little bit about radical substitution. I just gave the answer away. So let's look at it.
I have a question.
Go ahead.
Which one's polar?
The whole thing. Like this reaction going from here to here is polar. The mechanism, the way it happens is polar. All that means is that every bond I make, I'm transferring 2 electrons from one atom, and every bond I break, I'm giving 2 electrons to one atom. All right. Did that answer your question?
Yes.
Okay. All right, let's look at the next one. What do you think happened? Now let me help you to see it, because this is a skeletal form. What do you think happened there?
The hydrogen got replaced with.
So one of the hydrogens got replaced by another atom, didn't it? And we, by definition, what type of reaction is that? Let's go back up here. I gave you a definition for that. Amidst all of the other material. So do you see what it says? Something getting replaced by something else. Which one of those, which definition or which term does that fit?
Substitution.
Substitution. And if you go down here, you can see that's exactly what happened, right? One of the hydrogens got replaced by a chlorine. So this is it's a substitution. Now, the way it happens in this particular case, you can't do substitution on an alkane like that using a polar mechanism unless there's another type of leaving group present. Hydrogen is not conducive to doing polar substitution. So you actually have to do this in a radical fashion. So I'm going to show you really like a quick and dirty radical mechanism. We're actually going to study that radical mechanism in more detail later, but I'm going to introduce you to it now. Right, so for this is an example of what we call a radical. Right, so with a radical substitution, what do you think about bond making and bond breaking? How's it going to happen? Homo or hetero? Homogenic, homolytic, right? If it's radical. All right, so here, I'm going to add something here. I'm going to add plus HCl, and then I'm going to show a chlorine here and light. Y'all remember that equation from Chem? The energy of a photon, E equals h nu, where h is Planck's constant, nu is the frequency of the light.
No.
All right. All right. So the way this happens is it happens literally in 3 steps. And I'm going to run through this because we're going to talk about it a lot later. So it happens by first initiation, then propagation. Then there's another final step, termination. All right, so the initiation part happens when I take that chlorine and I cut it in half by beating it to death with ultraviolet light. All right, so I'm going to break this up into 2 chlorines like that, 2 chlorine radicals. How would I show that bond breaking homolytically like that? What would you do? What kind of arrows would you use and where would you put them?
You do single headed arrows.
Single-headed
pointing
arrows, good.
direction.
And where would I put them?
Between that sigma bond pointing the opposite directions.
Come on. That's exactly right. I'll break it like that. Homolytically, meaning each atom in the bond is going to get 1 electron. Go ahead, Tia.
What is that? Is that HV? What is on the arrow?
Yeah, it's a lowercase Greek n, so it's a nu. But you know my handwriting. You can write it as a V, because it does look like a V, but it's nu. It's the lowercase. It's lowercase Greek n.
Oh, okay. Thank you.
All right. So that's the initiation step where the chlorine gets cleaved in half. And now this is what we call our initiator. So that's going to go in and start doing a process in the next step that we call propagation. But the way that it happens, it's gonna do what's called abstraction. So these are the two hydrogens here. I'm gonna make one a different color. It's gonna be that plus chlorine radical. Everybody okay so far?
Yes.
So I want to break, this is how, and this is called abstraction. So we're removing H dot, not H plus. That's called proton transfer or deprotonation. But for abstraction, we're taking off a hydrogen radical. So I want to break this CH bond. I'm actually going to extend this bond out a little bit to make it more dramatic. Right? I want to break that like that and give one electron back to carbon. And then what facilitates this is the chlorine donating one electron to hydrogen, like so. Notice my arrows, all fish hooks, right? All single-headed, because all of this is either homolytic or homogenic, right? So after the propagation step, what I get is a new radical that looks like this. Got a radical on that carbon, plus what? Plus HCl. Do you see over here? Let me make that plain too. Over here, when this arrow, when these two arrows meet, you see that right there? That means that there's going to be a new bond between those two atoms. Sorry for the lag. Blame AT&T. Now their commercial says that their Wi-Fi is all this and that, and it's never lagging or dragging, but now we know otherwise, because this is not the first time that's happened, but that's a different topic. All right. So that those two arrows coming together like that means that I'm going to put a, I'm going to have a bond between chlorine and hydrogen. And then I'm left over with that radical at carbon. Everybody okay? Anybody not seeing that? Say something now.
I don't see it.
Which part? The HCl part or the CH bond breaking part or what?
Both.
Okay, so do you agree if I put these two arrows between this? First, let's go back. Do you agree that this right here is a carbon
Yes.
and it's bonded to that hydrogen?
Yes.
And if I put those two arrows in that bond, like so, it means that I'm breaking that bond and giving one electron to carbon and one to hydrogen. Yes?
Yes.
Okay, so then when that hydrogen leaves, let me go ahead and, when that hydrogen leaves as H dot, if I take the radical, the one electron on chlorine and donate it towards the hydrogen, that's going to make a bond between those two. So when this leaves, it's really leaving like as this.
Mhm.
And so you're adding that to this. Can you see that?
Yes, I see it.
So that's where the HCl part comes from. And then when I go back over here, you did agree that this one arrow going back to carbon means that it's picking up that electron, yes?
Yes.
So that's why I have this. Do you see that? The same carbon is right here.
Okay.
And now it has one electron on it.
Okay.
All right.
Thank
Yeah, good. I'm glad it clicked. All right. So now we come to the termination step, right? This is where the substitution part actually happens. So I'm going to start with this radical. I'm gonna put the hydrogen back because I don't want to confuse anybody. So that's that. Plus a chlorine radical. I just want to put those two together. How would I show it? And what type of bond formation is it? I want to put those together to get this. What would you do?
Could you show a single headed arrow going from the electron on chlorine to the carbon?
Towards it, yes. I also had to show that. Because with a homogenic process, both atoms are donating one electron. So I need an arrow from both sides. It just needs to be single-headed. And where they meet is indicative of the fact that there's going to be a bond formed between those two atoms. Right? So if I just drew one arrow from chlorine to that electron, that wouldn't be correct. Because if it's homogenic, both atoms are given one electron to form a bond. Let me fix that. All right. And then I'll put those in. Questions? Any questions about that? So that is it. That's a more involved substitution, you know, than I had planned to use, but it is what it is. It's a radical substitution. Other substitutions are much simpler because you'll have a better leaving group than hydrogen. But since hydrogen is not a great leaving group, the best way to swap it out is to do radical substitution. But we're going to talk about this a lot. We're going to talk about radical substitution on long chains and then study that in great detail. So don't sweat it if it's not clicking right away. But it is a substitution. All right, let's pick another one. We'll just go in order. Let's take this one. And then the two on the bottom we'll do together because they're both fall into the same category. All right, what do you think? Immediately, if I'm starting with a pi bond, what are my options? If my starting material contains a pi bond and that's where the reaction is taking place, what are my options?
Road and Glen Avenue in Auburn. Para continuar en español, oprima 9. Now, how can I help you today?
Pharmacist.
Okay.
That's not an option.
Prescription.
All right.
It's a substitution.
Remember, if a pi bond is the starting material, it cannot do substitution. It can only do, it looks like a substitution because my chlorine is swapped out with a hydrogen. But because it's a pi bond, a pi system, I can only do addition. And that's going to be followed by elimination. So let's do it. Let's show it. So here I'm going to add this, which is what we call a hydride. Right? It's a hydride. It's a negatively charged hydrogen. It's got a pair of electrons. It's a great nucleophile. So that I'm going to add that, right? So this first step is going to be addition. I'm going to add it to the carbonyl. And then what do you think is going to happen to that pi bond? Does it stay? Can it stay? Think about it. How many bonds can carbon have to itself?
4.
4. If I don't break the pi bond, how many bonds is that carbon going to have?
6. Wait.
It'll have 5.
Oh.
And that's only, that doesn't even exist in the Marvel universe with Thanos and all the characters, everything. We'll never have a carbon with 5 bonds to it. So anytime I add to a carbon that contains a pi bond, I have to break the pi bond. In this case, I'm breaking it and giving those electrons to oxygen. So I'm going to come up with this, in which I'll introduce you to another concept. Actually, you know what? I'm gonna do that. right? So when I add to a carbonyl like that, I always get this type of intermediate. It's called a tetrahedral intermediate. That's all, that's the result of addition to a carbonyl. So if you have a carbonyl carbon, whether it's a ketone or ester, amide, aldehyde, doesn't matter. When I add a nucleophile to it, I get this tetrahedral intermediate. Now, if I wanted to get here, what do I need to do? There's two things I'm gonna have to do in order to get to that product. I want to keep the hydrogen. What do I need to do to get to that product?
Eliminate the chlorine.
Get rid of chlorine. And what else do I need to do?
Make a double bond on.
Put the pi bond back, right? And just so happens that in doing one is going to facilitate the other. So if I put the pi bond back here, I'm also going to kick off chlorine, right? So that's going to give me this plus Cl minus, right? So that would be, what type of reaction is that? Where I reform a pi bond. Right,
Rearrange.
It's an elimination. Anytime I make a pi bond as a in my product, it's an elimination. Right? Eliminations always result in the formation of a pi bond. Additions always result in the breaking of a pi bond. Right? So you can see over here, I broke a pi bond by doing the addition step. And then I made a pi bond by doing the elimination step. And the reason I'm spending so much time with these few little examples is because this is foundational stuff. Like this is stuff that you're going to see over and over and over and over and over again. All right. So let's go back and grab those last two examples right here. So we've looked at every reaction type: addition, elimination, substitution. The only one we haven't looked at is which one?
Rearrangement.
Rearrangement. So let's look at these other two examples. We're gonna make that happen. Let me fix this first though, because I don't want this to get cut off. I'll fix it later. But I know it's gonna get cut off when I turn this into a PDF. All right, come on. All right, so we got two examples here, and we're not gonna have to go, I don't need a whole page for that, but we're gonna actually talk about a couple of concepts here. All right, so if you notice, if you look at this first example, both of these are examples of rearrangement, right, or migration of atoms or bonds across a molecule. So it's like we also could call it a shift. It's like a shift of a bond or a shift of an atom, shift of a pair of electrons across a molecule. So looking at that first example, what moved? Going from, let's say, let's call this A, and let's call this B. What moved going from A to B?
The hydrogen.
Good. See the hydrogen here, and then it moved here. And by the same token, let me put this in here because there's one hydrogen here that's not shown, right? Because it's a skeletal form, right? By the same token, what else moved? See how the plus charge was down here and now it's up here? All right.
So it lost an electron each time.
Yeah. So here's the rearrangement that this is an example of, is what we call keep doing that, hydride shift. A hydride shift. All right. So what I'm going to do is take hydrogen and both of its electrons and move them here to this carbon. Right. And so that's how that hydrogen gets shifted down. And then up top, you can see now, because I moved the hydrogen and the electrons, that carbon became positive because I took electrons away from it. All right. These hydride shifts like this, there's a purpose for them. A lot of times they happen in the case of trying to get to a more stable state, right? And so let me introduce you to another concept. So for cations, right? The stability trend for a carbon with a positive charge is make sure I'm using the tertiary, and I'll explain what tertiary, secondary, and all that means, but this is what we call tertiary. And then this is secondary. And then the one is primary. And then methyl. So this is the most stable. And then the methyl is the least stable. Right? And so up here, well, let me give you an example down here first. So a methyl cation would be something like this. Right? And then the primary cation would look like this. It would be a carbon with one bond to carbon. And that carbon would be positive. So the primary means that it's bonded to only one other carbon. All right. And notice the trend. The methyl is less stable than a primary, but a primary is less stable than a secondary, which in this case, I'm just going to add another carbon. Right, so now it's bonded to two carbons. This is methyl. This is primary. This is secondary. And then the most stable out of all of them is the tertiary. So I'm going to put 3 carbons on there. Or you'll see it written as 2', 3', or second degree, third degree, like that. Right? So carbocation stability, the trend is methyl is the worst, tertiary is the best. Right? So when you see something up here like this, you can see that this carbon here, what do you think? How many carbons are bound to that carbon that I highlighted in purple? Can you see it? Speak up a little bit. I think I heard you, but
Is it 3?
it's 3, right? You got a carbon here, you got a carbon here, and you got a carbon here. So that purple highlighted carbon is tertiary. I need to make my pen a little thinner. Right? Are y'all following that? And then the carbon on the bottom, how many carbons are bound to that?
I have a question.
Go ahead.
So it's tertiary because it's 3 carbons bonded to that carbon.
Yes, the one that's highlighted in purple.
Okay.
And then the one where the plus charge is, what do you think?
Is it 2?
2 carbons. It's got a carbon here bound to it, and it's also bonded to that carbon. So that carbon on the bottom is going to be secondary. Follow? Just stay with the example, and you'll see why the shift happened. All right. Now over here, that carbon up top is still tertiary. This carbon on the bottom, still secondary. What is the difference in those 2 cations? What's the for A? Is that, what's the bond order on that cation? Is it secondary? Is it primary? Is it tertiary? It's written as secondary. And we agree that it has 2 carbons bonded to it, yes?
Yes.
And then in B, that carbocation is now tertiary. Which is more stable? Based on what we just talked about down here.
Is it tertiary?
The tertiary. So a lot of times when you have a rearrangement, a lot of times rearrangements happen in order to get from a less stable state to a more stable state. So in the case of hydride shifts and things like that, they happen for stability. So now we went from I'll move that around because I need the space. So the shift occurred to go from what? A secondary carbocation to what?
Tertiary.
Tertiary, or more stable. Tertiary. Carbocation. I'm gonna put the carbo part in here too, because it's not just any cation. All right, so that shift happened to go from a secondary carbocation to a tertiary carbocation. And this is an example of what we call a hydride shift. So I took hydrogen and both of its electrons and moved it to the carbon that was adjacent. And this is a 1-2 shift. You can do, because the carbons are right next door to one another, but you can do a 1-3, you can do a 1-4. Like hydride shifts can be, it's pretty amazing, like how many atoms can be between the charges, the charge and where the hydride comes from, and it can still happen. All right, let's look at the next example, because that's also a rearrangement. What do you think? What happened there? That's a little bit more evident, isn't it?
One of the CH3 shifted and then the plus moved up.
Mm-hmm. So the methyl group shifted in this case, and then the plus charge is now on a different carbon. It happened for the same reason, but here, instead of a hydride moving, it was actually an entire CH3 group. You following? So this is also a rearrangement, but it's what we call a methyl shift. Let me fix that I. Right, so methyl shift, so the carbon and the electrons, right? Don't forget that part. You got to take the pair of electrons also. So the whole, basically the bond and the atom move to where that plus charge is. And again, this is a secondary, sorry about that. It's a secondary carbocation. And then when the shift happened, now I have a tertiary carbocation, which is more stable. So again, methyl shifts and hydride shifts, when they happen, those are rearrangements because you're moving an atom or an atom and electrons across space within the same molecule. But when they happen, normally it's to go from a less stable state to a more stable state. If that makes sense, I'll write that down here. If I can write. I'm just going to say to increase stability. All right, questions about the different types of reactions? The substitution, elimination, addition, rearrangement, any questions?
How does, when we're moving the groups, how does the other carbon become positive?
You mean the one up top?
Yes.
Yeah, so that carbon, if you look at it on the left side, let's call it A again. In A, that carbon has 4 bonds to it. And if I take a bond away, it's going to have 3 bonds to it. Right, if I took the bond, which the bond is composed of 2 electrons, right? If I move those electrons away from that carbon, it's going to become positive. It's going to become a carbocation. Because the valence is 4, and then if we do the formal charge, the actual is in B around that top carbon is 3. So 4 minus 3 will give you a +1 charge.
Okay.
And
Thank
it's the
you.
same on the bottom, right? There's a hydrogen there that's not shown. So for that carbon being secondary, right? It has 1 hydrogen and then 2 bonds to carbon. So it has 3 bonds to it already. That's why it has a formal charge of +1. And then when I move the methyl group down there, what's not shown is that, again, there's a hydrogen here. And it's over here too. Let me figure out a way to fit it in there. Right, so that hydrogen is still there. So that's why it has a plus charge. And then when I add that methyl group in, right now it has 4 bonds to it, so it's no longer positive.
I have a question.
Go ahead.
It's about one of the other problems. It was, can you scroll up?
Mm-hmm.
It was that one.
The addition followed by elimination.
Yes.
Okay.
It's about the tetrahedral.
Intermediate.
Yeah. Can you re-explain why the oxygen donated its electrons and then the electrons were like donated to that chlorine?
To the chlorine? Sure. So I needed to reform the carbon oxygen pi bond, right? Based on the product. Do you see that product where you have a CO double bond?
Mm-hmm.
So I need to put that double bond back to oxygen. So there are no electrons that can come from anywhere else to make that pi bond except for oxygen. because it already has 3 lone pairs. So I took one of those lone pairs and donated it to reform the pi bond. So that pi bond is going to be here, right? Is
Right.
that right?
Mhm.
And then at the same time, the chlorine, which is highly electronegative, and I don't need it based on what the product is, that there's a hydrogen there, not a chlorine. I need to break this carbon chlorine bond. Right, so that's all happening at the same time. So when I reform the pi bond, if I don't break a bond, that carbon is going to have 5 bonds to it. And that's not going to happen. That's not possible. So that carbon would look like this. Not to say I haven't seen something like that on an exam, but it's not possible,
Okay.
right? So I need to eliminate one of those groups. And those tetrahedral intermediates always, you're going to do one or two things. You're either going to trap it by adding in a proton or some other group to add to oxygen, or it's going to decompose like we showed and give you an elimination product.
Okay.
All right, does that make sense?
Yes.
Okay, all right, cool. All right, so we're going to stop here. I'll get these notes uploaded and all that stuff, and get the recordings uploaded. And yeah, we'll be back Wednesday, God willing, same bat time, same bat channel. Y'all don't know nothing about that.